Hello, ladies and gentlemen, and welcome to Mr. Saucedo's YouTube videos. Today we're going to be looking at electrochemistry terminology and how you can find the oxidation numbers for different elements. So to start with, we're going to look at oxidation. So oxidation is a process in which an element attains a more positive charge. So I also put in parentheses that also means that it becomes less negative, because depending on whether you're looking at a standard element or an ion or a whole bunch of other things, sometimes it's kind of hard to picture. Is this becoming more positive? And so sometimes it'd be easier just to think of it as becoming less negative. So oxidation, though, since it involves attaining a more positive charge, occurs when we are making cations like this. So we have our sodium as a solid. It is losing an electron, and now we have our positively charged ion. So notice this is oxidation because we have an element that is attaining a more positive charge as a result. Or, like it says, it's becoming less negative. It was neutral, now it's positive. So it lost a negative electron. So how are we going to remember this? We're going to remember this with the acronym OIL, okay? And obviously you know what OIL is, but the reason why we use OIL is because OIL stands for oxidation is losing. And specifically, what is it losing? It's losing electrons. What's the opposite of oxidation? So reduction is the opposite of oxidation. And that's where that's a process in which an element attains a more negative charge. Again, if you have an ion or something, sometimes it's hard to picture that. So just think of it as becoming less positive. Okay, so again, let's use another example that's pretty common. We've got chlorine gas here, and we're gaining 2 electrons, and we're making 2 chloride ions. So again, if we compare over here, it had no charge. Over here, it has a negative charge. It became less positive as a result of that because it gained 2 negative electrons in order to balance this. Now, how are we going to remember that? So the way that we remember that is with the word rig. So in reality, the big acronym would be OIL rig. Okay, you know what an OIL rig looks like? The rig part stands for reduction is gaining electrons. So we have OIL, oxidation is losing, and then we have rig, reduction is gaining. Now let's talk about batteries, since electrochemistry is often applied to batteries. So there are 2 main parts to a battery that we're going to be identifying right now. And so we have the anode, and the anode is the electrode where oxidation occurs. So again, when we're looking at electrodes, what we're talking about are the portions of the battery where you see those little positive or minus signs where it lets you know which side of the battery is going into which. So a good example of, again, an anode in this situation that we just wrote down is sodium. Sodium turning into a cation would be an example of an anode because this is by definition oxidation. So just to reiterate here, and at the anode, oxidation occurs. So picture an ox. So right here we have an ox, and just so you don't forget which one's which. So let's say that we have this portion of a battery. This is an anode. We have zinc. Zinc is losing electrons. And so as it loses electrons, what it's going to be manufacturing is zinc 2 plus. And so zinc 2 plus is an ion that's in aqueous solution. So the actual mass of this anode would start to go down as the battery gets used up. If you've wondered why batteries don't last forever, this is one of the reasons why. Eventually the anode will go away because it is slowly losing electrons. And as it loses electrons, all of a sudden you start to lose mass. And so what we have here is turning from a solid anode to now becoming part of an aqueous solution. What's the opposite of an anode? The opposite of an anode is a cathode. A cathode is the electrode where reduction occurs. And so again, we have our chlorine gas turning into chloride ions. So the way to remember that is a red cat. So we have an ox and we have a red cat. At the cathode, reduction occurs. And so right here we have copper, which would be on the opposite side. So picture these wires were connected. We have our zinc on this side, we have our copper on this side. The copper is gaining electrons. And so what that is doing is it's turning the copper 2 ions that are in aqueous solution, and it's forming copper metal. So as it forms copper metal, the cathode increases in mass as the reaction occurs. So as the battery is being used up, the anode gets smaller, but the cathode starts to grow in size because the electrons are settling now and turning the ion into a solid substance. So again, remember, you can picture reduction as becoming more negative or as becoming less positive. So we're going from a +2 to a 0, to just neutral copper, which would be, again, a good example of reduction. All right. So just to reiterate, we've got a galvanic cell, which is a fancy word for a battery, the standard batteries that you're used to. It's a device that stores chemical energy and turns it into electrical energy. And so this would be like one side of your battery. This would be the other side of the battery. So what do we need to know? The anode is negative. It is giving away electrons. And so remember, we have anox. So this would be our negative part of our battery. Okay, the cathode would be considered the positive part of our battery. And so that means that it says giving away electrons. It's actually gaining electrons. And so the electrons are going to be flowing from anode always to cathode. So we're always going from this way to that way. Now, the confusing part that always makes people a little upset, but it's because of an old definition, is even though the electrons are going from the anode to the cathode, in reality, the current flows from the cathode to the anode, and that's because of an old definition. And because it's such an old definition, when we finally realized that it ended up being the opposite, no one wanted to change it because that would have meant that all old literature involving batteries would have to be redone. So instead, now people just kind of know that, okay, great, even though the electrons are moving this direction, the current, like the electrical current, is defined as going from this side to that side, okay? And so again, it's just, I know it doesn't make a whole lot of sense, but it's just because of an old definition.